So in this video, I'll be talking about three precision position motion synthesis, specifically analytical synthesis. And you might look at the problem of trying to hoist a canoe onto the roof of a vehicle, and perhaps we want a mechanism to do that. Now I could have just two precision positions, but you notice I have that intermediate precision position that helps guide me through that path. Well, that's why we would want to go to a three precision position problem. So first of all, recognize that as I add this extra vector loop equation, I am removing one of my free choices. We saw the same thing when we did it graphically, where we went to a third precision position. I was only able to choose my moving pivot, not the location on that perpendicular bisector. We get the same thing going on here when I go to a third precision position. I get one fewer free choice in my system of equations. So the natural question is, why am I trading that away? Just like I said, it's really providing this intermediate position that helps guide the motion. Very often we know clearly where we want it to start and end, but guiding it through the intermediate area also helps. Sometimes we have a problem that requires three very carefully placed precision positions as well. So it might not just be a guiding location. It might be a very hard prescribed third precision position. We'll move on later to talking about why a fourth position and even why a fifth position. So we can keep adding more positions, and we find that we trade away free choices for those extra precision positions. So let's now move to actually setting up the problem. I'm going to start with a base 4 bar, and let me start off by just saying I am going to have precision position 1 right here. I'm going to move then to a second position and a third position. Note that I'm only looking at one side of my mechanism right now, but the same thing would apply for that W star and the Z star, the right side of the mechanism. Just to keep things a little bit cleaner, I'm going to only look at this left side. So I'm going position 1, I'll go to position 2, and finally position 3. I can describe the motion between those, or the displacement between those positions with my displacement vector. So I've got delta 2 going from position 1 to 2. And then going from 1 to 3, I've got my delta 3 vector. And then I also need some rotation angles. And the rotation angles that I'm going to have, first of all, I need to define my W vector, which is going from the ground pivot up to the moving pivot. From the moving pivot up to the precision point, I have the Z vector. The W vector is rotating by the angle beta. So in this case, I would have, let me put this angle down here. This would be beta 2. And going from first to the third, this would be beta 3. Similarly, I have the rotations of Z. You'll notice that I'm trying to measure an angle that is, or a line that's parallel to the initial Z. So this angle of rotation right here would be alpha 2 from the initial Z. And then from the initial Z here, I've got alpha 3. So this is then what I need to start formulating my standard form equations. So just like we did previously, I'm going to go up the displaced side of the mechanism, come back down the undisplaced, the W and the Z, and form these standard form equations. I've got from the first to the second position, and then first to the third position. So now I have two standard form equations, and now I can start to calculate or count up how many knowns, how many unknowns. So first of all, scalar equations. I've got two vector loop equations. Each one of those has x and y components, so each one is equal to two scalar equations. So I have a total of 4 scalar equations. Prescribed in motion generation, I've got my delta vector, so I've got delta 2 as well as delta 3. And then I have my rotations of the coupler, alpha 2 and alpha 3. Finally, how many unknowns do I have? Well, my unknowns are again the link lengths, the W and the Z. Each one of those has magnitude and angle, or x and y components. So I've got W and Z, as well as the rotations of the input link, the beta 2 and the beta 3 angles. So these guys are also unknowns. So I've got beta 2 and beta 3. So when I start to add all these up and say how many equations, how many unknowns, I have my unknowns, I've got 2 in W, 2 in Z, because they're x and y components, and then 3 and 4 as far as beta 2 and beta 3. So I've got a total of 6 unknowns, and I've got 4 equations. So I need to make 2 free choices. All right, so let's talk about how we solve this and what to make for these free choices. So I've got this system of equations. What am I going to pick? Now, in graphical motion synthesis, we went ahead and picked the moving pivot, which was equivalent to picking the Z vector. I could do that same thing here. We also looked at picking the ground pivot and using my X and Y free choices to pick a ground pivot and ground pivot specification. We'll do that in a little while analytically. I'm not going to do either one right now. Instead, I want to make this as simple of a solution as possible. Now notice if I picked any, so my unknowns here, I've got my w's, my z's, as well as the rotation beta 2, beta 3. If I was to go ahead and pick the z vector, my unknowns now are in the exponents of beta 2 and beta 3, making these nonlinear equations. So what I would want to pick to make this a linear system of equations is if I go ahead and pick my beta 2 and I pick my beta 3, now my unknowns are w and z, and they're multiplied by knowns in the parentheses. So this makes it a much easier system of equations to solve. It's now a linear system of equations. So with that said, how do we solve it? Now there's a whole host of ways to do this. You could plug it into your calculator, you could use MathCAD, MATLAB, Maple, a variety of elimination methods, some optimization methods. There's a variety of ways to solve this. The easiest one, and the one that we'll focus on primarily in this class, is plugging this into matrices, and usually then using MATLAB to solve this. So what I'm going to do is take this system of equations, these two vector loop equations, and put them into matrix format. So this matrix format looks like this. I've got this coefficient matrix right here. I'm multiplying this by my unknowns, my w and my z vector, and then I've got my product matrix on the right. So I can now code in my coefficient matrix and my product matrix into whatever solver that I want to use, and then I can solve for my unknown w and z, and therefore have a solution dyad for 1/2 of this 3 precision position motion problem. I then repeat that same process for the other side of my mechanism, the w star and the z star, and then I take those two dyads, put them together, and I can make a 4-bar that then will move through my 3 precision positions. So we're going to use this and now build on it in class and actually do some practice problems where we will synthesize 3 precision position mechanisms.